Welcome Mechanics of Materials students. In this lecture we're going to discuss strain displacement relationships for rectangular coordinate systems. So just to recap, we're looking at displacement fields as described by a Greek letter lowercase delta. Which is going to be a function of where you are, x, y, and z. And then we'll be looking at resultant or associated strains, remembering that we can express strain as a tensor, as Greek letter epsilon subscript ij, so we can have exx, exy, etc., representing normal and shear strains, with I and j going from 1 to 3 for xyz, for 3D. Okay, so if we have a point, some point on a body at a given location, x, y, z, we have a 3D, if we're looking at a 3D condition, which we're going to for the most part, unless we're specifically stating that we have a plane strain condition. Displacement is going to be composed of 3 different parts. So we're going to look at the total displacement function as having an x component and a y component and a z component. And we can think of these as some kind of function, probably a continuous function, that basically says, okay, wherever you are, x, y, and z as an independent variable input, we're going to take you somewhere else. Another x, another y, another z. So an x prime, y prime, z prime, according to some function. Could be any function. Could be you go nowhere. It could be 0. It could be a constant. But there's going to be one that moves you in the x direction, in the y direction, in the z direction, depending on the function, linear, quadratic, periodic, whatever, some function, and where you started. So those are the 2 things. So x moves you, or u, displacement function u moves you somewhere in the x direction, displacement function v moves you somewhere in the y direction, and displacement function w moves you somewhere in the z direction. So for an example, if u, v, and w were all constants, they were position independent, the displacement that we would end up describing would be translation or rotation. We wouldn't have any strain. So all of the points would stay the same distance from each other throughout whatever the displacement was. So we will be looking at things where that's not the case, since we're going to be looking at strains in this section. But that's just an example of how displacement functions can create certain types of motion. Plane strain conditions. What if one of those is 0? So if we have no strain in one orthogonal direction, whichever one it is, all the other strains are constrained to the other 2 orthogonal directions. We have what's known as plane strain. So the normal strain in that 0 direction would of course be 0, but all of the shear strains that have a component in that direction would be 0. So nothing's moving in that direction. So in this case, a displacement function for plane strain in the xy plane wouldn't have a w component, would only have a u and a v. And our strain tensors, our matrices, would be simpler. Nothing in the z column, nothing in the z row. So no shears, no normal strain in the z, and the shear components also 0. Okay, oddly enough, in order to achieve plane strain, about the only stress condition that we can't have is plane stress, because we achieve plane strain by pushing or pulling on our body in every orthogonal direction, making sure it doesn't move in the direction that has no strain. So typically plane strain is going to be found in areas that are highly constrained, so the middle of big parts at the center of a part, or if we have biaxial or triaxial stress states, so we're not letting things move. Oddly enough, that tends to be where we have fracture as opposed to yielding type deformation. If you remember our discussions of stress, we'll tend to have plane stress where there are no forces, so free surfaces where there is a lower state of constraint. Thin sections will tend to be in plane stress, thick ones in plane strain. You can think about it as, in order to not move, you have to have something pushing, and if you're in a thin section or a free surface, normal to that thin section, there will be nothing to push. Okay, so now we're going to get into some math, and what we're going to do is we're going to look at the ways these displacement functions u and v take a point at a given starting position, operate on it to move it to another position, and then how that tallies up with surrounding points that are also being operated on by a displacement function u and v to carry it to a new position. And looking at the relationship between the starting position of a couple of points and the ending position of a couple of points in terms of u and v. And we are going to be referring to this diagram back and forth for the next, say, 3 pages. So there'll be a lot of going back and forth. I may have to move the page, adjust it back and forth a few times. So you can always see that diagram. We'll be referring to our starting and our ending points on a body. So let's introduce you to points P, Q, and R. We are on some kind of body. It's a deformable body. It's not rigid. There's an origin to the coordinate system down here. And we've got some points of interest P and R and Q somewhere on the body before deformation. These are located before deformation. They're located, point P is located at XP. So we move over from the origin XP, and here we are at the x coordinate of P. P is located at Y sub P before deformation. And then point R is located at XP plus delta X in the versus the origin, and at YP versus origin in the Y. And then Q is located just at XP in the X, but at YP plus delta Y in the Y. So we have a delta X, delta Y offset in the X and Y respective directions to define the location of R and Q versus P. Okay, we have some displacement event. We put some stress on this part and it strains, and that strain is seen in displacement of P. P ends up at P prime. So in order to get P to move to P prime, it's operated on by displacement functions u in the x and v in the y. So we can say the displacement of point P is function u operating on P in the x direction plus v, function v, our displacement function v, operating on P in the j. So another way of saying operating on point P, because remember u and v are really only functions of your starting position, well, operating on point P means operating on whatever was at that starting position denoted by point P. So another way of saying the displacement of point P is to say u at xp,yp in the I hat direction plus v at xp,yp in the j hat direction. Their u and v are probably different functions. Likewise with R, we're going to start at looking at P and R and their relative movements. So R moves upwards a little bit differently than P because it started in a different place. And that's something to remember. U and V are functions of both x and y. So this wasn't a translation at all. So R went to R prime, so it didn't go to R double prime. It went up, and so apparently V has some V moves you upward more if you're at a more advanced position in the x direction when you start. Just another way of saying u and v are functions of both x and y. So we can describe the initial position dependency of our displacement of point R by just saying, well, where did it start? So u, displacement function u operating on point R, we can describe it as u operating at xp plus delta x, which is the x location of point R, comma yp, which is the y component of point R, and then v, displacement function v, is doing the same thing. So if you'll note, the only difference between the displacement of point P and the displacement of point R is the different starting x location of point R. So different input to those displacement functions are going to give you a different output. So if we want to relate the displacement functions based on their starting positions, we kind of note that we have the same function and we have an x and then we have an x plus delta x. So this is the math makes sense once it's pointed out to you, but this is starting to look a little bit like the beginnings of the definition of derivative. It's like if we subtracted those two and then divided by delta x, took the limit as delta x got small, we'd have the rate of change of u with respect to x. First derivative of u with respect to x. If we take that and we look at the Taylor series analog, we can write this, first couple of terms of a Taylor series as the function of x plus delta x as the function at x plus the first derivative of the function with respect to x times delta x. So just basically look up Taylor series expansion of any function, and this is what you have. So let's apply this to function u, our displacement function in the x direction, and just say, hey, let's let u operate on x plus delta x. So we'd say, okay, u at x plus delta x is, in this case, our x of interest is xp. So we'll say u at xp plus delta p, comma yp, which is our starting position. Notice there's no delta on y, so it just tags along. And that's going to equal the function at x, which is x sub p, y sub p tags along, plus the first derivative defined at the initial position, x sub p, and then we have our delta x. And again, we're only taking the first two terms. Neglecting those higher order terms is accurate when we have small delta x's, which is the case for strains. So everything is small. So let's take a look at another way to name these. So if we look at u at xp plus delta x, of course, that's u at point R. This is u at point P. And this is the rate of change of u with respect to x. So we'll drop in these other definitions later. We can do that same kind of Taylor series substitution for the displacement of q versus displacement of p. So we can end up writing the displacement of point q is u functioning at q in the x direction plus v functioning at q in the y direction, which is the same thing as u at xp plus comma yp plus delta y. So same thing as r, except we've got that different starting position of delta y for q versus p. So otherwise the same. And again, applying the Taylor series expansion, we have this starting position of q equals starting position of p, first derivative of u with respect, now this time to y, times delta y. So again, we're looking at how, just at the beginning, we're just looking at u. So how does q move to the x in the x direction based on the fact that it was in a different starting y position before the deformation? Quick pause. Okay, so far we've been focusing only on the xward displacement, the u portion of our displacement for r and q, moving to a different r prime, q prime, simply because they were in a different x and y position before they started. So we're going to continue looking at that. Now we're going to zoom in on the line p prime, r prime. So we're going to start doing our little flipping back and forth. I'm going to simplify this a little bit. Give us a little bit more room. We're going to be, again, referring to this figure quite a bit. So we're looking at our post-deformation position now. So we're looking at this P prime to R prime right here. And so we're going to take a look at how it relates to this angle alpha here versus the horizontal. So we can say that, of course, its real length is if we considered the angle, it would be, we'd have to use Pythagorean theorem and say P prime minus R double prime squared plus R double prime to R prime squared, take the square root. But for a small alpha, we can say that, well, P prime to R prime is pretty close to the cosine of alpha. If alpha is really, really small, cosine is practically 1. So we can say that P prime R double prime and P prime R prime are pretty darn close. So we can just simply use the x location of R prime and P prime. So the x location of R prime is just R double prime. So basically that's saying we can take just the x component of that and say that's, that longer length is equivalent. Okay, so now we're going to go back. Now we're looking at saying, okay, we're defining P prime R prime, which is the new length of line PR. So think delta L over L0. This is the new longer length, P prime R prime. So we're kind of got one foot in the game of defining strain. So, and we've kind of done a little approximation, neglecting that small alpha. So now we can relate P prime, the length of P prime R prime, to some things that our function U operated on. So we've got x, the x position of R prime minus the x position of P prime. This is going to be approximately equal to the length of P prime R prime. Okay, so we can write x R prime in terms of xr and that U displacement function operating on R. In fact, that is the new x location of R. It was its original location plus whatever the U displacement did to it, and the same thing with P. That was part of our original definition of the operator U displacing things based on their original position. Okay, so let's hold that thought and remember now we can go back to that Taylor series definition. So we kind of got a three-way here. We've defined P prime R prime, then we've defined XR prime and XP prime. Now we're going to go back to our Taylor series definition and say, well, we can also rewrite U operating at R in terms of U operating at P and this first derivative, and substitute both ways. So we're going to substitute this in here, and then we're going to substitute both of these in here and write P prime R prime with the two-way substitution. So we end up with our new PR length after displacement as the x location of R plus our displacement function U operating at originally at P plus the first derivative with respect to x of that operator U times delta x, the original length of PR before deformation, minus XP plus UP. And so we can do some rearranging there and write this as just XR minus XP plus first derivative of U with respect to x times delta x. So we were able to basically, we had a UP and we had a minus UP, so we got rid of those two. Simplified a little bit. Now, x, the x location of r minus the x location of p, those were the original positions of r and p, which we defined as delta x back. So we're going to do a lot of flipping. This delta x right here. Okay. And go back and forth. Okay. So we have p prime r prime equals delta x plus first derivative with respect to x times delta x. Now we can relate p prime r prime as that longer length after strain. So we can relate that to our strain in the x normal direction, our EXX. And we can define EXX as the limit as our delta x goes to 0. Remember, EXX was defined only for infinitesimally small lengths. So we'll just, okay, let's make it infinitely small by making delta x go to 0. Of p prime r prime minus pr, the original length divided by the original length. So in this case, PR is delta x. So if we do a little algebraic wrangling of this expression and that expression, we get this, which we can end up subtracting, canceling those two terms, and then these two terms will cancel, and we get an expression that basically says the strain, normal strain in the x direction, is the first derivative with respect to x of that displacement function that takes us from one place to another place in the x direction, the u displacement component of our overall displacement function. So first derivative with respect to x. If we did that whole argument, that whole derivation in the y direction, we'd be looking at how that v component of the displacement function operates, and we could find that dv dy ends up being equal to our normal strain in the y direction. So if we had general displacements, if we had a way to measure displacement at different positions x and y on a part that was subject to some kind of load, we could use that and got a function x and y, a function u and v based on different x and y points. We could use those functions, take the first derivative, and calculate our strains. So if we had general displacement, so we had a z component, so we were measuring a w displacements at different z locations, x, y, and z locations. We could get that same relationship for EZZ as being the first derivative of that z displacement component with respect to z. So now we found a way to go from displacement. So if you measure how far something moved, an original point versus a final point at different locations, so you can construct a function based on your original location. You can now take the first derivative of that function and get strain, which would, as long as that function is still applicable, would apply, like for instance, between the points that you measured. So that's only normal strain though. So we need to take one more step, apply these same kind of ideas to get shear. And for that, not surprisingly, we're going to use an angle. So we're going to go back to our figure, and we're going to take another look at that angle alpha that's defined by r prime, p prime, r double prime, which is that lower angle alpha. So let's just take a quick look at that. So we've got alpha here is r prime, p prime, r double prime. Now if alpha is really small, we know that alpha is approximately equal to sine alpha. And so by properties of right triangles, we know sine alpha is r prime to r double prime, that the opposite side of the triangle divided by the hypotenuse, which is p prime to r prime. Okay, so we can define that as here's our sine theta, which is sine alpha, which is approximately equal to alpha. Again, for very small displacements, we can also, at this point, make the approximation that P prime R prime is equal to PR, which would make that denominator delta X. Okay, so we're going to hold that thought. Alpha is equal to R prime, distance between R prime and R double prime, divided by our original PR X distance. So we know that R prime, the length of the y direction length between points R prime and R double prime is just simply the difference between the y coordinate of R prime and P prime, because R double prime and P prime have the same y, right? They're on the same line, the same y. So the y coordinate difference between those two is the same as the y coordinate difference between these two. That's going to get us a little further mathematically. So we can relate now the y coordinate of R prime to the y coordinate of R before deformation, plus that displacement operator V moving R to a new y position, which we can then relate with that Taylor series first two terms as that V operator operating on P plus the first derivative of V with respect to X, delta X, and likewise. So we can do the same thing over here. Excuse me, not. We're going to leave that one alone. It's already defined in terms of P. We wanted to define displacement at R in terms only of displacement at P. Excuse me. Getting to be a lot of R's and P's here. But bear with me. After we derive this, we will use these displacement versus strain expressions without having to go back to the original derivations. But it's pretty important to know where they come from, because otherwise it's really easy to use them out of context. Okay. Before deformation, P and R were on the same line y from a y standpoint. So go look at that. So P and R were separated by delta X, but they had the same y coordinate. So we're going to go back to that. Before deformation, the y coordinate of point R and the y coordinate of point P were the same. So if we subtract them, we're canceling terms, and we have the V operator, the V displacement operating at point P minus the V displacement operating at point P. Those two cancel. So we end up with only this term in this expression equal to R prime to R double prime distance. So that whole expression simplifies to this. Okay. So if we put this up here for R prime, R double prime, we divide by delta X goes away, and we're left with alpha equaling the first derivative of V, the displacement that takes you some to a new y coordinate with respect to X, as opposed to first derivative of V with respect to Y, which would have given us the strain in the normal strain in the Y direction. Okay, we can walk through that same argument when looking at angle beta up here between point P prime and Q prime. Because remember, if we're looking to get engineering shear strain, we have to look at both of angles alpha and beta, because we're looking at the displacement of two different points to define shear. So if we do that same routine, that same derivation, but we apply it to angle beta, we end up getting du dy. And we remember that our engineering shear strain is alpha plus beta. Both of those angles result in that originally right angle change. So we just sum those two, and we show that in this case the strain, the engineering shear strain xy is going to be equal to dv dx plus du dy. And we could define the same thing in any plane that was on that had plane strain. So using a plane strain argument at any other plane. So if we were in the xz plane, our engineering shear strain would just be du dz plus dv dx. So basically, just think about it as the opposite term from the one that you would normally apply or normally think of that displacement operator moving you in. Of course, the displacement operator depends on everything it operates on, x, y, and z, but it takes you in a given direction. And again, remember that if we want to get from these engineering shears to our tensor shear, that we would divide by 2. So we have the 1/2 relationship. So we've just related displacement defined as a three-way function, u operating to take you somewhere new in the x direction, v to take you somewhere new in the y direction, w to take you somewhere new in the z direction, all three being dependent exclusively on what your xyz position was when you started, and just looking at ways to geometrically relate your original and after deformation position. We used a little bit of math. And then we're able to get relationships between strain and displacement. And in most cases, here's a summary of what we just did. So this is what we'll be using for the most part. And obviously, this will be the most useful when we have continuous functions. So we can just take a derivative if we need to go from displacement to strain, or integrate to go from strain to displacement. That's definitely the most handy. But of course, if we don't have continuous functions, we can always take measurements and use things like mathematical integration, numerical integration, or other numerical techniques to apply these same relationships, even if we can't just do something with a continuous function. Okay, so quick break. Okay, we're going to do a quick example just to make it a little bit more concrete here after all of that math. So suppose we know from measurements at multiple points on a part that we do indeed have continuous functions for u, v, and w. So our u, our displacement in the x direction, is going to be based on the cube of x and some sinusoidal function of z, and linear with y times that sinusoidal function of z. Kind of crazy, not quite sure what would do that, but somebody measured it. V is linear in each of the different original coordinate terms, and we have a declining exponent, inverse exponent, and cosine for y, or excuse me, for w. Kind of every function in the book. And a, b, c, l, and y0 are all constants. And somebody wants to know, what is the state of strain? So state of strain means what is the combination of EXX, EYY, EZZ, and the 3 shears. So that's all we need. So basically all we have to do is start taking derivatives. So to get our normal strains, we're going to take derivative, we're going to take the x derivative of u, the y derivative of v, and the z derivative of w. And these are of course partial derivatives because we have multiple different variables, but of course that's easy. All we do is basically hold everything that is not the variable with which we are differentiating constant. So we take the x partial of u, and we're going to end up getting 3a times x squared. This term has no x terms in it, so it goes away. So we just get 3ax squared. We're going to go ahead and take the first derivative with respect to y and z because we'll need those for shears. So first partial derivative of u with respect to y, this term goes away. That's just a constant, so we end up getting b sine z over L. And the same likewise with z. This time we're going to actually have to deal with the trig function. First term goes away again. So by just sits as a constant multiplier. And then we'll end up getting cosine times 1 over L. So we get by over L cosine z over L. We do the same thing for the other two displacement functions. So we now have all the tools we need to construct our shears and just state our normal strains. So normals are going to be partial of u with respect to x, partial of v with respect to y. Look, it even looks like a matrix. Partial of w with respect to z. And then for our shears, we're going to do, we're going to have to combine. So shear in the xy plane is going to be that plus that. Shear in the xz will be these two combined. And then shear in the yz will be these two combined. Kind of looking right across the matrix there. So this is written out algebraically. So xy will be the b sine z over L plus czy, and so on. So this is the state of strain at any point. And notice it varies by point. So if we were going to relate, and this is important to know because again, if we were going to look ahead, this is jumping ahead a chapter, if we were going to need strain for some reason to say calculate, well, what is the state of stress at that point? Hey, I have some elastic properties, some material properties. If I put in the points of interest or maybe figured out where strain was a maximum over a certain range of points, then that would give me an idea where stress is a maximum and where I might be likely to break. So understanding state of strain or stress as a function of where you are is super useful, because then you can figure out points where things might get interesting and prevent it from getting interesting, if that interesting means yielding or failing when you didn't want it to, which is most of the time. Okay, what if you want to go the other way? I've stated many times that most of the time you measure displacement and then infer strain. Well, sometimes you go the other way. There are some methods where you will measure strain directly and then want to know, okay, given this state of strain, which is dependent on my position, what's the actual displacement? Maybe I don't want something touching. I may know the strain, but depending on where I am, I want to know if this point is going to actually move so far from a given reference starting position. So I might want to go back the other way. So no problem. If we had displacements, u, v, and w, we got to strains by taking derivatives. We can go from strains to u, v, and w by integrating. And the only trick comes is when we have a few constants of integration. So we're going to start with an xz plane strain example. So xz plane strain means no strain in the y. So EYY and the two shears that have y components are all 0. So we've got normal strain, which is a function of both x and z. Somebody measured this. We have parabolic function, we have normal strain in the z, which is another parabolic function, and we have shear strain, engineering shear strain, zx, a linear function. So okay, if I have exx and I got a function and I want u, I integrate with respect to x. Shouldn't be too hard. So I integrate ax squared and I get 1/3 x to the third. I integrate a z squared with respect to x and I get a z squared x. And then I get a constant of integration. Now, because I got a couple of variables here, I can't just write like a constant, because remember, if I had a function only of z and I took the first derivative with respect to x, it would go be 0. So I have to assume that I could have some function of z out here that, that would be, added to my function displacement in the x, u. So u, which is a function of x and z, is a over 3 x cubed plus az squared x plus some function exclusively of z. Now I do the same thing for normal strain in the z direction to get w. I integrate EZZ with respect to z. So EZZ was just a z squared. So I'll get a over 3z cubed plus some function exclusively of x, and I'm going to call it f2 because I want to make sure I remember that it is not necessarily the same function that was operating on z up here. It could be, but we don't want to assume it is, so I call it f2. But we do know it's operating exclusively on x because if I took the derivative with respect to z, it would go away. So it is a constant of integration, even though it's a function. Okay, and now I'm going to look at the shear, same way. Shear is first derivative of w with respect to x and first derivative of u with respect to z. And oh, happy day, since I started with the normals, I actually have expressions for u and w. So I'll just integrate those again, but with the opposite variable. So I'm going to integrate a over 3z cubed plus some function of x with respect to x. Okay, so end up getting that. So first I just start by writing, back up. I'm going to start by writing it as stated in the shear expression, and then I will integrate it. So if I say shear is first derivative of w with respect to x, then I take my expression for w and I take the first derivative with respect to x. So since my first term here has no x, it goes away, and I'm just left with the first derivative of f2, which is a function of x with respect to x. I do the same thing with u. So I end up with these two terms equaling this. Well, I was given that up here that my shear in the zx was this. So this plus this equals that, just by the definition of shear stress. So I end up with dw dx plus du dz, which is both of these, equals that. And as it turns out, we can cancel those two, and we end up getting a situation where we can say that our derivative of f2 with respect to x, that's an x, equals negative the derivative of f1, which is a function of z with respect to z. That looks a little odd and not so useful, but if you think about it, it turns out that this is only true if both f2 and f1 are true constants. So we can call them c's. So we start with that relationship. Now we get around to integrating with respect to x. I was doing it a little prematurely up there. So I conclude from here that the first partial of f2 with respect to x is a constant, and the first partial of f1 with respect to z is a constant, but opposite sign. Now I integrate f2 with respect to x, and I end up getting c1x plus another constant, a real constant this time, we'll call it c2, and then I get, of course, negative c1z plus a third constant. So this is the real trick to going from strain to displacement, is because we're integrating, having to keep track of constants of integration that can be functions of the opposite variable. So basically all we have to do now is take these two functions and plug them back in up here and here to get our two expressions, our u and v. So here we have those two. And again, the shear we pretty much already had in terms of these two being constants. So we could just say those two constant functions equals 2azx. So that is it. That was a little bit of squirrely math. It won't always be that complicated or necessarily that simple, but effectively 2 integration steps, and we use the shear expression to evaluate the 2 constants of integration. So at the end of the day, the power is going to be having both displacement and shear. If you have one, you can get the other, provided you have an integratable or a differentiable continuous function to work with. So that is it for a very long, very mathy lecture. But now we have some very powerful expressions relating displacement in all 3 orthogonal directions to shear, normal shear, or to strain, normal strain and shear strain for any deformable body. So that is it for this lecture, and for the next lecture we'll be taking the same consideration and looking at changes if we're working in cylindrical coordinates.